Hi, today's lecture is on limiting reagent stoichiometry. It's nearly lunchtime. I'm getting hungry. However, I left my lunch at home. I'm going to quickly hop into the car, drive to Stop and Shop, and purchase ingredients to make a peanut butter and jelly sandwich. I buy a loaf of bread, a jar of jelly, and a jar of peanut butter. I come back to the school and I start to make my sandwiches. The number of peanut butter and jelly sandwiches that I can make is 100% dependent upon the ingredient that I'm going to run out of first. Most people, when they're making a peanut butter and jelly sandwich, use 2 slices of bread, approximately 1 tablespoon of jelly, and approximately 1 tablespoon of peanut butter. Given that recipe, the bread is the ingredient that I'm going to run out of first. That, to chemists, is referred to as the limiting reagent. The limiting reagent. The limiting reagent is defined as the reactant that dictates or determines the amount of product produced because we run out of it first. In other words, after all of my bread is gone, I'm still going to have some jelly and some peanut butter left in the jar. The jelly and the peanut butter are called excess reagents. Let's look at another analogy. What if I have a junkyard filled with tires and I want to build my own car? Well, despite having these hundreds of tires available to build cars with, I only have 1 car frame. The number of car frames that I have is going to determine the number of finished cars I'm able to produce. The car frame is the limiting reagent. As soon as I run out of car frames, I can no longer manufacture cars. The tires, on the other hand, are my excess reagent. I have so many of them, I'm not going to run out. Let's define that. The excess reagent is the reactant we have so much of that we won't run out. Paper car. So how is that relevant in a chemical reaction? Same thing is true. Let's say I want to do the chemical reaction to produce aspirin, and I have 10 grams of all the ingredients to make aspirin. As soon as those 10 grams of one ingredient runs out, aspirin can no longer be manufactured. So whatever reactant I run out of first is going to limit or determine the amount of product that I'm able to make. Looking at this first word problem, take the reaction. Nitrogen trihydride reacts with oxygen to produce nitrogen monoxide and water. In an experiment, 3.25 grams of nitrogen trihydride are allowed to react with 3.50 grams of oxygen. Question A, which reactant is the limiting reagent? Part B, how many grams of nitrogen monoxide are formed? Part C, how much of the excess reactant remains after the reaction? Well, let's tackle this first part. Which reactant is the limiting reagent? Despite the fact that the question prompt asks us specifically for the limiting reagent, I would like to take a minute to explain to you how you were able to recognize that this is a limiting reagent problem. As you go back to the data that you're given in the problem, 3.25 grams of nitrogen trihydride, which is one of the reactants, and 3.50 grams of oxygen, which is the other reactant. That visual or that fact that you've been given information about both of your reactants is the number one clue that this is a limiting reagent stoichiometry problem. We have to first figure out which of these two reactants is going to be depleted in order to predict how much product is able to be made. So to answer that first question, which reactant is the limiting reagent, we must determine, using stoichiometry, and I'm going to abbreviate stoichiometry Stoich, S-T-O-I-C-H, and I'll put a little asterisk because I'll need more room for this. We're going to set up a scenario. What if I use all of the NH3? How much of the oxygen will I need? We ask, do we have that much? The answer to that question is either yes or no. If we do have that much, then the NH3 is the limiting reagent. If I don't have that much, then oxygen is the limiting reagent. Here's what we mean. If I use up all the 3.25 grams of nitrogen trihydride, or ammonia, how much oxygen will I need? Well, we know that our chemical reaction, or our recipe, tells us moles. We're given data in grams. So the first thing we'll have to do is change the gram data to moles. Right, that's my math for the molar mass. And that value will be 17.04 grams. Then I want to convert moles of ammonia into moles of oxygen according to the balanced chemical reaction, and I did double check that the chemical reaction was balanced. Oh, no, I didn't. Let me double check this. There's one N, 3 H's, 2 H's. It looks like I'm going to need a 3 in front of here to get me to 6, which means I'll need a 2 here. So that means I'll need a 2 in front of nitrogen monoxide. And now for my oxygens, 3 and 2, oh, that's only 5. So now I'm going to need to double everything. Four N's, 4 N's, 12 H's, 12 H's, 12, 13, 14, 15, 16 O's. Oh, and when I look at that, the numbers 4, 8, 4, 6, they can be reduced by 2. So 2, 4, 2, 3. Those are really my coefficients. So we have 2 moles of NH3 for every 4 moles of oxygen. Doing the math, I get 0.38145 moles of oxygen. Oh, nuts. I need to go one more step, because when I'm asking how much oxygen will I need, the data for oxygen is given to me in grams. Okay, so let me just keep going with my stoichiometry for a minute here. Now that I've got moles of oxygen, I'm going to convert the moles of oxygen into grams of oxygen using the molar mass. And I have 12.206 grams of oxygen needed.
Thank you.
The question is, do I have it? Well, the amount I have is 3.50 grams of oxygen is what we have. What I need is more than what I have. Therefore, oxygen is my limiting reagent. Now that I've determined my limiting reagent, I'm able to answer how many grams of nitrogen monoxide are formed. I'm going to use, so since this is my limiting reagent and the nitrogen trihydride is my excess reagent, I ignore the data for the excess. I have so much of it, I'm not going to run out. I'm only going to hyper-focus on the information for my limiting reagent, because once I run out of it, I can't do anymore. So 3.50 grams of oxygen, and now I do stoichiometry regular. 32 grams is for every 1 mole, because we've got a diatomic situation. For every 4 moles of oxygen, we're able to produce 2 moles of nitrogen monoxide. And for every 1 mole of nitrogen monoxide, we are able to have 30.01 grams of it. Right, that's our molar mass. Doing the arithmetic, 3.5 times 2 times 30.01 divided by 32 times 4. I have 1.64 grams of nitrogen monoxide will be produced. The last part says how much of the excess reagent remains after the reaction. Well, the excess was the nitrogen trihydride. That's how much we had. So we're going to need to figure out, it's basically how much you have minus how much you used. That tells you the amount in excess. We have 3.25 grams. I'm now going to redo the stoichiometry to figure out how much I've used. So that's the 3.50 grams of oxygen, and I do all my stoichiometry out with oxygen. It's 2 moles of NH3 for every 4 moles of oxygen, and there are 17.04 grams for every 1 mole. Oh, silly me. That fraction needs to be reversed. .32 grams per mole. 3.5. 0.93 grams of NH3 were used. To figure out how much is in excess, we take what we have, 3.25 grams of NH3, subtract from it how much we've used, 0.93 grams, and the difference, 2.32 grams, is how much is in excess. How can these problems get harder? Well, let me just show you one. I won't work through it here. We can save that for class. One way we can make this a little more challenging is if you're not given the chemical reaction. If you're just told what your two reactants are, and then boom, you're left alone. So now you'll have to predict the products, balance your chemical reaction, and go through the motions of solving it. The last thing we're going to talk about in this lecture comes up in question number 3. As we look at this chemical reaction, the question asks, what is the theoretical yield? And then they give you in part B the actual yield and ask you to calculate the percent yield. Let's start with the word percent yield. Percent yield is asking us basically how much of the reaction and the products did you produce in the laboratory. And as we all know, we're humans, and when we're in the laboratory, things are not perfect. So what we're comparing here is the actual yields to the theoretical yields. And to get it into a percent, we're going to multiply that ratio by 100. The theoretical yield is the stoichiometry you'll do on paper. Because this is theoretically what we're supposed to get if everything in our universe works perfectly. The actual yield, though, is what happens in lab. I know we haven't done any labs ourselves this year, but if you think back to your previous experiences in lab, sometimes things spill. Sometimes there's splattering. Perhaps some of the residue is left behind in a beaker as you're pouring the contents from a beaker into a graduated cylinder, let's say. So we tend to lose things, or maybe if our species was wet and we needed to dry it before we massed it, if we didn't let it dry all the way, now we have extra water molecules in there, so our matter is heavier or higher than it's supposed to be. There are things that happen in lab that are not perfect that we can, upon reflection, suggest how we would change the procedure or what we would do differently next time in a second or third or fourth trial to try to get the data as close to possible as to the theoretical yield. So again, I'll wait until we get together in class to review how to work through these problems, but I need you to have the notes on what percent yield, actual yield, and theoretical yield are. Thank you for your time, and I look forward to working through these and more problems with you when we're together in class.